Hey everyone, thank you for joining. We're gonna wait maybe just 1 or 2 more minutes to let people slowly trickle in. Please let me know in the chat if you're having any issues hearing or seeing anything. And hopefully we can get started pretty soon. Awesome, thank you. Can someone let me know if the slides are being cropped on one side, or if you can see them all right? You can ask in the, just write in the chat. All right, thank you. Give it 1 more minute and then get started. So everyone knows this is being recorded, and the recording and the slides are going to be made available on the resources page of our website. So you can go back and take a look at all of this after the fact, share it around. All right, I think we will go ahead and get started. So my name is Seth Wiesman. I'm a solutions architect with Ververica. I'm really excited to be giving this webinar today on troubleshooting Apache Flink. So we are the company founded by the original creators of Apache Flink. Along with supporting a lot of the open source development, we also provide a number of tools to help bring stream processing into the enterprise. I'd just like to let everyone know that Flink Forward San Francisco is coming up. It's a 2-day event with 1 full day of training, which includes some introduction to stream processing, SQL, and a more in-depth version of what we're going to be covering in this webinar today. And day 2 is a whole host of keynotes and technical talks by Flink production users. And for joining in this webinar, you can get 15% off with the code below. Okay. So this webinar is really about going from development to production. We work with a lot of customers bringing stream processing into the enterprise. And I'd like to cover some of the common stumbling blocks and things that we see people struggling with when building a robust application on top of Flink. I have gone ahead and written a very canonical streaming application. So suppose we have a lot of IoT data that's being generated as JSON and written to Kafka. Our job is going to read and deserialize those records, enrich them from some third-party service, perform an event time-based window aggregation over that data, and then finally write it out to 2 different syncs. There is the first sync that just simply takes the data from the event time window, and a second that performs a secondary aggregation based on the same key but non-windowed over that data. So I have this job running in a local Flink cluster, and we can see that it's stuck in this restart loop. So it starts up, it runs for a moment, it fails, and then restarts again. A good first place to look when your job is failing is just under the exceptions tab, and this will tell us exactly which exception caused the last failure in our job. And it looks like Jackson failed to deserialize some JSON, and so it threw an exception. I will note that some of the errors in my job are rather trivial, but it's really about discovering and correcting that we're looking at today. So we need to understand how Flink handles exception handling and how it handles the failure case. So in any distributed long-running application, you are going to experience failure. It's just a fact of life. And Flink has world-class fault tolerance and error handling. This is through our checkpointing mechanism. So periodically, we take a globally consistent snapshot of the state of your application at any particular point in time. so that if the job ever fails, we can restart from that checkpoint and resume processing. If your source is also stateful, like most of them are, such as Kafka, we can then reread whatever records were produced after the last checkpoint, so we get exactly one state semantics. Oh. No, I'm just showing the I'm showing the Google Docs slide. What was I saying? So we can restart and reprocess those records. What this means in practice is you get exactly once state semantics, meaning we're going to process the data and produce the correct results as if we had never had any failure and every record had been seen exactly one time. Where this can potentially create an issue is if we fail due to bad data within our stream, such as an invalid JSON record, which is a fairly common thing in practice, we're going to fail on that record, restart the job from the last checkpoint, and then reread that same bad record, fail on it again, and get stuck in this infinite loop. In practice, we should really only throw exceptions on fatal errors, such as out of memory or no disk space, things where the only solution is to try and reschedule the job somewhere else and try again. But for bad data within our stream, we should consider looking at logging, metrics, or other side outputs. So, okay. Can someone let me know if they can see my IDE? It should be working now, yes. Thank you. Okay, so I'm inside of my job, and I have this JSON deserialization schema. What we're doing here is simply reading the bytes that are being consumed from Kafka and deserializing it using Jackson. The issue here is that we're not handling bad reads. And so we're throwing them into the runtime and simply causing a restart. In practice, bad JSON is a very common situation, and so we should handle this in a more graceful way. We'll start by catching the exception. In practice, you should probably use the more specific exception that Jackson provides. But for right now, we'll just assume that anytime it throws, it's because there's bad data. And when using a deserialization schema, you can simply return null, which means I failed to deserialize. Let me just skip this record. And so the null will not be propagated downstream, it will be filtered out. And so the rest of your operators and your business logic only see the valid data. We could also consider adding in some logging here and potentially some metrics to have some greater insight into whether or not things are failing. But for the purposes of right now, simply filtering out the bad data is going to solve the problem and keep us from failing continuously on these bad records. So I am going to go back into my job, and we'll go ahead and deploy this new version. So in just a second, we should see this deploy into the Flink cluster. And if we did this properly, we're going to find that we're no longer stuck in this restart. And that's exactly what we can see, right? So the job is running continuously, data is flowing through as soon as these metrics show up. If we wait just a second, because I would actually like to look at some of these numbers. What we're going to see is that records are flowing out of Kafka and into our next operator. Let's see if we can get this to run. All right, I think the Flink cluster, along with running Zoom, is putting a little pressure on my laptop. But what we would see if we looked here is that data is flowing into this operator, which is our event time-based window, but it is not leaving. And if we click on the watermarks tab, we can see that there are no watermarks being generated in this application. I'm going to cancel this so my laptop can cool down a little bit. Oh, And now you can see the metric. So data was being generated, it was going into the window, but never going out. We know that with event time, it is propagated by using watermarks. And we noticed that there was no watermark available for in our string. The question is why? And we need to first look at what can cause watermarks, how watermarks are generated, and what can cause them to stall. So in any stateful event-based system, we follow the same basic pattern. An event arrives at time t, specifying when it occurred in the real world, and we perform some computation and write it into states. When the watermark arrives, a special indicator record flows through our string. It says it is now time t, meaning that if a record arrived for 1 o'clock, we'll set a timer, and then when the 1 o'clock watermark arrives, that means we can now fire that timer because it is now 1 o'clock and all records that should have arrived before that time period should have already arrived. Of course, things may arrive late and we can handle that. And that's where we can specify some allowed lateness into our window, saying, look, I know things should arrive on time, but if they show up to 10 minutes late, I'm okay with that. Beyond that time is when we may start to drop records because we do not want to hold things in state indefinitely, as that is akin to a memory leak where you would just keep eating up memory until you have nowhere to put your stuff. The way watermarks are calculated is by taking the min of the maxes. So assume this blue box is my window operator, and I'm running my job with parallelism 4. That means I have 4 parallel partitions reading from my 4 Kafka partitions, each producing data and sending it into the window. Each of those are going to track the max timestamp that it has seen so far and propagate that downstream. The window operator is going to keep track of the max timestamp it's seen for each parallel partition and say that the global watermark is the minimum value across all of those. So as data begins to propagate through the string, we're going to start tracking maxes for each parallel partition. Once we've seen a watermark for each partition, we can start calculating a global watermark. As a new max for each partition arrives, we can check and see if there is an updated min. Every time we get a new watermark is when we'll start to fire event time-based timers. So when this watermark of 10 is calculated, that means any event time timer from time 10 or earlier can now be fired. The issue arrives when we have idleness within our system, meaning that there's a parallel partition that is not carrying any data, and so it is not generating watermarks or advancing the watermark in any way. So it is going to stay as the min in our event time window, and so the watermark never advances. The watermark assigner needs to be able to detect idleness and artificially advance the watermark. And this has to happen based off of processing time because, again, there is no data flowing through the system to push records forward. There are a couple different ways we can handle this, but the most important thing to notice is that advancing the watermark artificially has to be application specific. There is no silver bullet here. It just depends on what is going to work right for your system. So a couple options are to trail the current processing time. Say it is 1 o'clock and a partition has gone idle, right? We have determined that we haven't seen any data for a particular amount of time and it is now idle. And we also know that in the best case scenario, right, if everything was running properly, no record should show up more than 5 minutes late, then it's a safe guess that the watermark for that partition should be at least 12:55. And we can keep advancing it in that manner. We could also advance continuously from the last known watermark. So again, if I see a watermark that says it's 12 o'clock and no new watermarks have arrived for a particular amount of time, I determine this partition is now idle, then I could advance the watermark by 1 minute each minute until I see a new record. The best place to try and detect watermarks within your idleness within your stream is at the source, because that is the one place within the system in which you can look into the producer that is generating your data. And you can know for certain that your system really is idle. There are no records to read at this time. Any source can mark itself as being temporarily idle, which tells downstream consumers that that parallel partition should not be used in watermark calculations. But maybe our source doesn't know how to mark itself idle, somebody else wrote it, or we don't have a way of looking into that producer and determining that it is idle in any meaningful way. In our data stream, we can call rebalance prior to assigning timestamps and watermarks, which does a round-robin repartitioning of the data across all parallel partitions. So as long as one data is coming in somewhere, we'll guarantee that there are records in all partitions, and so all partitions can continue to advance the watermark. And again, this advancement is going to be based on some processing time heuristic. Currently, there is not a clear way of defining this in Flink. You need to do it yourself. You can't just specify an idleness timeout, but it is something that the community is very interested in implementing, and there are some open tickets where we're determining the best way to add this functionality. So let's go back into the code base. And I have, again, this troubled streaming job. We're reading data from Kafka, and what we've determined is there's one partition within Kafka that periodically does not see any data for long periods of time. There are a couple ways that we could handle this without going into the Kafka consumer itself. The first option is that I could reduce the parallelism of just the source. So I know that there are 4 partitions in my Kafka topic, and I also have been running my job with parallelism 4. I could have just the source run at parallelism 2, which means that each reader is going to consume from 2 different partitions, because I feel pretty confident that there's always going to be at least 2 partitions with data in our system. Once it goes down to the timestamp assigner, this is still running at parallelism 4, so our data gets properly redistributed, and we get to take advantage of all of our horizontal parallelism. The issue here is that I've really hard-coded something into our job. It may be that most of the time, all 4 partitions have data, and I really need 4 parallel readers to be able to keep up with the flow of data. I may also determine at some point in the future that I would like to increase the number of partitions in my topic to 8, but I'm still stuck here with parallelism 2. If I increase the parallelism of my job to 8 as well, the source would still be stuck at 2, and suddenly I would have 2 readers, each reading from 4 partitions. It's not very scalable. Let's not do that. Instead, we may look inside of our timestamp extractor. And I'm using the bounded out-of-orderness timestamp extractor, which keeps track of the max timestamp it is seen for each record. So along with assigning a timestamp, it also keeps track of the max, and periodically propagates that downstream as the new watermark for its parallel partition. This works pretty well, but what will happen is if we stop seeing data in a particular partition, it's just going to keep periodically outputting the same watermark that is now stale. We could instead use a punctuated watermark assigner. So instead of having data be produced periodically, we get to specify the watermark and when we'd like to propagate it forward. In this case, we could now set a timer and determine, hey, it has been 5 minutes since I have seen any data in my stream. I should go ahead and propagate a artificial watermark downstream. And by doing this, we have the maximum amount of control on how we want to control event time in the idle case of our system. So that is by far the most powerful way to solve this problem, but it is also a little involved. The last thing that we could decide to do is to simply go right here and call rebalance. And so this says every source We're going to have 4 sources, each reading from 4 partitions. But then I want to do a round-robin repartitioning of this data in my stream so that every parallel partition is guaranteed to see data as long as somebody is consuming data. And this is certainly the simplest way to solve the problem in a scalable manner. And it actually works for most scenarios. As we'll discuss with serialization later on, Flink has a very cheap network compared to other systems. And so doing a rebalance is not a performance bottleneck by any means. So once again, we've gone ahead, we've made this change. I'm going to go ahead and redeploy the job. And while we're waiting for that to come up, please, if you have questions as we're going along, ask them in the chat. We'll try to get to them as I have time, and certainly at the end, we can cover any questions you may have. Okay. So, as we can see, we've added the rebalance into our system, and data is flowing through. So I'm going to hit cancel again because, again, this is just a little much for my laptop. But when we see the metrics flowing through, we find that things are moving. Things are leaving our event time window. So we feel good, right? We have data flowing through, and we have seen that at least looking at this metric, right, watermarks, is a good indicator of what is happening within our system. But we'd like some more metrics. I would like to have greater insight into what is going on with my system in production so that I know if there are issues. Let me pull my slides back up again. So Flink has very advanced metric system. And we can think of metrics as just being a pair of identifier and measurements. We have 4 basic metrics types in Flink. There's a counter that can always count up, right? Keep track of the number of records you have seen, and potentially count down depending on the metrics reporter you're using. So something like Prometheus does not allow counters to go backwards, but InfluxDB does, for say. We have meters, which allow you to track the rate of change within your system. So you can see how often some event is occurring. Histograms give you a nice overview of the distribution of your data and frequency that different events occur. And gauges allow you to expose arbitrary values. So worst case scenario, if the other 3 metrics types do not work, you can always just expose something as a gauge and show off an arbitrary value. As I mentioned, these are exposed via metrics reporters, which give you integration with all the major metric services. So InfluxDB, Prometheus, StatsD, whatever you're using in production, Flink likely supports out of the box. We also support metrics through Flink's REST API. So you can query the job manager and get a particular metric out. And this, in fact, allows us to visualize metrics in the Flink UI. So maybe not the way you want to show off your graphs in production, but they definitely give you some insight, particularly in development, if you don't want to be setting up a whole system. Out of the box, we provide quite a few number of metrics, particularly all the things that you would want to see when managing a JVM in production. So CPU usage, memory, threads, garbage collection, we can look at class loading and I/O, and also more Flink-specific things such as checkpointing, throughput, and latency. And so when you have metrics, you typically want to use some of them to create alerts, things that inform you, hey, something is not running properly, we should probably take a manual look at our job. The basic questions you want to be asking when running Flink in production are, is my job making progress, right? Am I keeping up with the flow of new data? In Kafka, this might be referred to as the consumer lag. And Flink forwards the native metrics from each source client to Flink's own metric system. So you can, for instance, get the Kafka client metrics directly out of Flink. We don't need to go through some third-party path. We also want to know, are my tasks making progress? And the watermark is the best way to identify this. I generally believe that the watermark is the single most important metric that you can track in Flink, right? If you're only gonna look at one thing, that would be the one to pick, because it tells us if we are keeping up with data and if data is properly flowing through the system. We can even look at the watermark at each individual subtask and see if one is holding things back. So say we have operator A and we query its watermark and determine that, you know what, it's keeping up pretty close to processing time. So we feel good that it is closely following a stream of data. On the other hand, operator B, which consumes from operator A, has a very low watermark. It is not keeping up with the current processing time. And so this one seems to be having trouble following the flow of data, and it's likely the bottleneck in our system. So we know this is the place to go and optimize. And finally, we want to keep track of our checkpointing. So checkpoints in Flink, as we mentioned, are how we handle our failure recovery. And so if checkpoints are not completing, we have an issue, right? We cannot recover from disaster. Some general things to keep track of are the last checkpoint duration. So you'll typically notice in production that checkpoints take the same amount of time, typically. And so if your checkpoint normally takes 10 seconds, a checkpoint that suddenly takes a minute might indicate an issue. Also checkpoint size, right? The amount of data that we have stored within states. When you're done with data in Flink, you should be removing it from state, clearing it. Otherwise, we'll build up state infinitely, which is akin to a memory leak, right? And finally, just keep track of the number of completed, failed, and in-progress checkpoints. 1 or 2 failed checkpoints is actually not that big of a deal. Checkpoints have a timeout duration, and it may just so happen that there is a spike in traffic within your system, and we're really busy, and a checkpoint cannot complete in time. But after that spike dies down, the next checkpoint does complete successfully. You know what? That's absolutely fine. If we start to see a large number of failed checkpoints, that's when we may want to consider looking deeper into our job and understanding what is taking so long. So certainly we have all of these great built-in metrics, but I'd also like to add some for our own job, right? I want to make sure that my business logic is behaving in the way that I expect it to. And I mentioned earlier that we are enriching our data with a third-party service. So our JSON records, contain a location, which we would like to query some third-party API to determine the current temperature at that location, add it to the record, and then forward it downstream. It may so happen that this third-party service is periodically unavailable. And that's okay, right? We don't control the system. And this is sensor data. 1 or 2 failed records is probably okay, right? If we just throw it away. But a lot of failed records is not. And so certainly we're handling the error case so far as we're catching the exception and preventing ourselves from failing the job. But we're not indicating to ourselves in any way other than logging that something has gone wrong, right? Tracking your logs is a very inefficient way to notice errors. They should be for debugging purposes. So I'd like to know how frequently we're failing to hit the service. And that is exactly what a meter is for. So I'll declare a new meter within our system, and we'll call this failed queries. We will instantiate it within open, which means that it gets created for each instance after it's been shipped to the task managers. And we'll go ahead and create an instance of this meter. So we're inside of a rich function, which gives us access to the runtime context that has a large number of extra capabilities that we can add on top of our system. One of those is getting access to the metric group for this particular task. So I can get the metric group, which are all the metrics scoped to the task, and then I can register metrics in it. I can even add subgroups so I can scope any of my business logic specific metrics. And so that's what I'll do. I'll add a new group called temperature client. Within this, we can now register our meter. So I have this meter, and we'll call it failed requests. And we'll go ahead and register. Now we can just use this. So inside of our exception, right, we have failed to make this query. I'll go ahead and mark it. And so say I'm using Prometheus in production, I can now track this metric and determine, hey, if I see more than 2 failed requests in a 5-minute period, I would like an alert. I would like to be able to I would like somebody to manually go and check what is going on. So make sure this is not running, okay. And we'll go back to the slides. So we have our job running, right? We're running, data is flowing through the system. We have the right metrics, so we feel like we can peer into the system as need be and understand what is going on. And we start to run some, bigger tests. And I notice that one of my sinks is outputting incorrect data. As I mentioned before, we're performing 2 different aggregations on our system. The first one is an event time-based window that takes these records, keys them by location, and then says for a particular windowed amount of time, calculate the average temperature at that location. We're outputting that downstream into a sink, but we're also performing a second aggregation that rekeys by the same location, but does not include a window. And I would like to keep track of the max average temperature I've seen for any particular location across all time. And what we're noticing here is that we're constantly outputting smaller and smaller values. So we suspect that we're actually calculating the min and not the max. It's a simple mistake. We can go in and fix it, but as good software developers, we also know that we would like to add a test to our system so that we can both verify that we have fixed the problem and prevent any regressions in the future. And the Flink community strives to provide the right tools for both unit and integration testing. So we understand that stateful stream processing is becoming a more integral part of the enterprise, and having correct systems and validating those systems is incredibly important. In general with Flink, you can think of there being a pyramid of testing. We have our stateless functions, such as the deserialization schema that we looked at earlier. We have stateful functions, like this max operator that has to constantly keep track of the max temperature that it has seen so far. And then we have integration tests, where we're actually deploying a job against a cluster. And we have tools to help with all of these. So when you just have a basic stateless function, such as the deserialization schema, there's nothing Flink specific that we need to consider, right? You can simply instantiate an instance of this function and start pushing data through using typical JUnit or your test framework of choice, validating that data is being, in this case, deserialized properly or not deserialized properly if it's an invalid record. At the other end, we have integration testing. And certainly before deploying to production, we should run our job against a cluster at scale and QA test it and do all those good things. But we're also going to want to do some automated integration tests. And we provide out of the box this mini cluster with client resource, which can instantiate a local Flink cluster within your test framework. And so it's a class rule inside of JUnit, meaning it's automatically set up and tear down for you, even if the job fails. And we can configure this in exactly the same way that we would configure our job in production. So we have access to all the different knobs here. And then within our test, we can simply get the execution environment and deploy a job. And it's going to be deployed against this local cluster. It may be that we run with a special sink that knows how to validate the data within our stream and see that, yes, we are outputting correct results. This cluster can be used against multiple tests, which is incredibly useful because you're going to find very quickly that setting up and tearing down the cluster takes up the most time in your test framework. And so by being able to reuse this infrastructure, you're going to make it easier on yourself, and you're going to make people more likely to write tests because it doesn't take 10 minutes every time you run Maven test. But then we have what's in the middle, which is testing stateful user functions, stateful or time-based user functions. And that's what I'd like to focus on here, because I think it is the thing that people tend to skip over the most. They unit test their stateless functions, they run integration testing, but very often people skip this step. And so we have what are called test harnesses that allow you to push events and time updates into the operator. We can then observe how the state and time changes as we push these events through and verify the correctness of our outputs. And so these are actually used internally to verify the correctness of Flink's built-in operators. So the window operator and process functions and all those goodies that we like to use are verified using this exact same framework. So you can feel confident that it's looking at the right things. The one thing we have to note are the different layers of abstraction within Flink to know what we're testing against, right? So at the very top, there are user functions. And these are the things that we're used to looking at within the Flink runtime, or within the data stream API, right? Your maps and your flat maps and your filters and so on. At the bottom level is the Flink runtime, which is your cluster. And it's the thing that we're looking at when we run integration tests. But in the middle are stream operators, which are how a data stream is implemented under the hood. So the window operator and process function and so on are implemented as stream operators. This is the thing that manages your state backend or registers and fires timers. If we're looking at stateful functions, we have to be cognizant of the stream operator layer. And so once again, I'm going to go into the system and I'm going to very quickly check out a different branch. Okay, so I have this test, and I would like to write a stateful test of my measurements, of my average temperature, max average temperature. So I can have calculate max average temperature, right? I can create a function, just instantiate it. And if I tried to use this out of the box, because it is stateful, right? If we look at it, because this is stateful, it has a value state that is registered in the Flink runtime. And every time data goes through, we're going to go ahead and check and say, if we have a new max, please go ahead and update the state and output that downstream. If we go into our test and we just tried to run this, we would see that it failed because we haven't set up a runtime context. And if we tried to mock out that runtime context, we'd very quickly realize that that's a very hairy endeavor. And it's we'll be mocking out a lot of internal details that may not be stable across even patch releases, right? These are the implementation details of Flink, which we're not interested in testing. I just want to make sure I'm interacting with my state in a good manner. So I'm going to go ahead and wrap this in its corresponding operator. So this is a flat map, and so its corresponding stream operator is a stream flat map. I'm going to copy these generics over and just go ahead and wrap it. We can now go ahead and use a test harness. So I'm going to pick the keyed one input stream operator test harness because this is a keyed stateful function. And just to make sure we can see it, I'll do this on the next line, is equal to new keyed one operator test harness. So I can pass the operator. I'm going to go ahead and pass the key function, right? So it knows how to take the key, get location. And we then also need to pass the type information for the key type. So I know that this is a string. Now this thing is ready to go ahead and use. I can open it up, which opens up the test harness and runs open, initializing the runtime context and registering our states. We can then go in and start to push records through. So I can process an element, where I can pass in both an element, I'll just use null as a placeholder, and also the timestamp associated with this. So if we were using event time timers or doing some other time-based operation, we can make sure that we have a ready set timestamp associated with each element. Once we do this, we can then get the output, so we can see, did this thing output anything after processing the record? We can check the number of state entries. So I know that when I write my first elements into this operator, it should add it to states. And I should see that there's one element written into my state backend. The same note, if I know that something should be clearing state or deleting it from my state backend, I want to be able to remove that. Let's see that this has gone back to 0. We can also interact with time. So I can say process a watermark, right? Let's say that we push this element through and assigned a timer, set a timer for time 100. I can now update the watermark to be time 100 and see that, yes, my timer fired. That's an implementation detail, not something we should necessarily be testing. But I can see that my operator does the right thing and test what happens when a timer fires. We can even set the processing time so we can manually move the processing time forward and test those timer firings as well. This allows us to write strong unit tests that can validate the business logic of these stateful operators, which is typically where the most interesting business logic in a Flink application resides. So our job's running, right? And we'll feel really good about that. We have metrics, everything is going out properly. It's time to do some performance tuning. And what you may have noticed is that I was using JSON everywhere within my system because that's what I was reading in. But it turns out that is a very inefficient way to run with Flink. And we'll talk about why. So Flink has its own type system. It's what we're talking about when we refer to type information. And it's how Flink determines how to serialize and deserialize a record. Serialization turns out to be the biggest bottleneck within a system, within a Flink job. And so it's the first thing we want to consider when optimizing our application. There are 3 different serialization points within our stream. There's ingestion serialization, where we read data out of, say, a source or write it to a sink, and we need to serialize in some very specific way, right? That was our deserialization schema we looked at earlier. And that is almost always user-defined, right? I need to be able to specify this data is coming out of Kafka as JSON. There is wire serialization. So as data is shuffled across the network, say during our key buy, it needs to be serialized and shipped to a different task manager. And there is state serialization, when objects are written to and read from state or into and out of our checkpoints. And these two use the same serialization scheme that is typically derived by Flink, or can be specified explicitly by the user. So Flink has a very expressive type system and a large number of built-in types. We support all the primitive types, tuples, pojos, Scala case classes, and Avro, right? So if you are using any of these, Flink is going to use an incredibly efficient serialization schema, and we feel pretty good using it. But if nothing else works, it is going to fall back to using cryo. The issue is, cryo is incredibly slow. So we ran this benchmark of the different serialization schemas by implementing this pojo using the different formats. And what we can see very clearly is that the tuple and pojo serializers are incredibly fast, and cryo is very slow. So what we would like to do is avoid cryo as much as possible. This can be handled within your stream by, let me go ahead and check. I'm going to check out the right branch. And so there's a couple things we'd like to do. First of all, I updated my serialization schema to now deserialize into a pojo class. And a pojo is defined by a Java class that has a no-art constructor and getters and setters, the standard bean pattern. But nothing else changed, right? I just updated all my code in the various places to use this instead. And what we're going to see if we run this job and we run some benchmarking is that it might be an order of magnitude faster than it was before and running an order of magnitude more efficiently. So we're absolutely getting the most out of our cluster that we could possibly see. If we want to absolutely make sure that we never fall back to cryo, we can actually go into the config and disable generic types. This means Flink will fail the job submission if your data stream uses cryo at any points. So we can enforce these semantics at compile time. And if your class that is being stored in state or shipped around the through the stream is not one of the valid types, it's going to give you a big error and say, hey, you need to fix something. And so we can enforce these good semantics and have the most performant application possible. The last thing that I want to look at is backpressure. So backpressure is when a downstream operator cannot keep up with the flow of data from upstream producers. In that case, it is going to propagate backpressure, which is Flink's way of slowing these operators down. And it is absolutely the right thing to do because it keeps your job running stably. But it's also a sign that things are not as performant as they could be. And so Flink detects backpressure by actually looking at stack traces of your job, because there's a specific point within the runtime in which it stalls out the upstream operators. And so we can check and say, see, is it spending a lot of time in those locations? And again, you can look at this through the Flink UI. So you can click on the backpressure tab. And if everything's great, it's going to give you a bunch of green lights. But if there's high backpressure, we know that we should probably look into this. And backpressure propagates from downstream to upstream. So again, I have operator A that feeds into operator B. B cannot keep up with A, which means it is going to exert backpressure on operator A. And we're going to see the backpressure there. So why might that be happening? Once again, we'll go back to this enrichment where we have some data that's flowing through, we extract a key, we use that key to enrich that record in some way and then ship it downstream. Ideally, we would like all of the data and do this enrichment fully within Flink, right? So we have two streams that we connect in some way, either by keying both streams or by using a broadcast state pattern. But in the real world, that is not always possible. Sometimes data is from a third-party service, and we need to be able to interact with that in a proper way. So my client, when we're pulling this temperature, is hitting some external service. And it turns out that most of the time, it is just waiting on that service to return, right? So there's a lot of stalled out time. And so it is pushing back pressure on the upstream operators as it's waiting for data to flow through. This absolutely will dominate the latency and throughput of our stream. So instead, we would like to be able to do this asynchronously, where we make a number of requests to the database and then ship them downstream as they finish. And to do that, Flink has an async function pattern, where so long as you have a client that can support asynchronous requests, the API is going to handle all the proper integration. So integration within the data stream API, the proper fault tolerance, so we can still get our exactly once semantics, the proper ordering of elements, because sometimes order matters, and the proper handling of event time semantics. So data that arrived on time does not suddenly become marked as late because the watermark somehow overtook it, as we're now using multiple threads. Once again, going back to here, we'll look at our enrichments. And so I have a flat map function, but I'm going to replace this with a rich async function. And if we go ahead and implement this class, right, we now get this async evoke. I'll take this, copy all my business logic down, and need to make a few quick updates where we're updating the temperature. Instead of doing this, I'm going to look at my temperature client, and I determine that it has an asynchronous an asynchronous call. So it's going to return back a Java future. And so when it's complete, I'm going to go ahead and just use this, the temperature. Excuse me. And this actually has two pieces. There's the temperature and the exception. And I'm just going to go ahead and copy this in. So we can say, if E is equal to null, there was no exception, then go ahead and say input will set the temperature, everything went great, and we'll collect it in our result future. So we'll complete this future. With our input. And if it was not null, right, there was an error, just as we saw before, we'll do exactly what we did last time and copy this, managing everything. So we're still marking the event, we're still doing our logging and keeping track of all these good things. But now we're running this asynchronously, and so we can make multiple requests at a time, but still keep all of Flink's really good management guarantees around state, default tolerance, and so on. Okay, so I see that we are running towards the end of our time. So I would like to open it up to questions if anybody has any in the chat. And we can try to dive into or clarify anything that we discussed that you did not understand during the presentation. Okay, so if there are not any questions, I would like to thank everyone for joining today on this webinar. As I mentioned, everything is going to be, this was recorded, the slides and the recording are going to be made available on our websites, and love to see you at Flink Forward in San Francisco, April 1st and 2nd. Please feel free to use this promo code to try and to get a 15% discount on your ticket. Thank you everyone for joining.